Okay, so we're on to day 6 of Physics 210. Today we're talking about forces. And the first one we're talking about is we have an elevator. And this elevator we're going to think of as just a box hanging on a string. So we've got a little elevator here. And with this, we are also starting with free body diagrams. So we can do a free body diagram with our box, and we can say that the forces acting on this elevator is we have some force due to gravity, or force weight, or often I will just write mg, because our force gravity is mass times gravity acting down. And we have some force tension, so something pulling our elevator up. So we've got free body diagram with 2 forces on it. Note that you could also do a free body diagram just by changing that entire elevator into a dot and say that we have mass times gravity acting down, and we have our force that's pulling it up acting up. I like pictures, so when I've got space and time, I'll normally draw out what's going on. So this is my overall piece. We're told that an elevator has a mass, so let's get the corner. What I know is that the mass of my elevator is an elevator has a mass of 5,000 kilograms. 5,000 kilograms. It is operated by a lift that has a force of 60 kilonewtons. So force, and I'm going to call this force max. This is how much force this lift can provide. We'll see in a second as we go through our different solutions. It's not always necessarily providing that. So 60 kilonewtons, which is going to be 6,000 newtons, 60,000 newtons of force. Determine the force required. So we're now on to our what to find. Determine the force required to hold it in place. So force, we're going to call this force at equilibrium, is our first thing we're asked for. We will ask if it's going to go a maximum of, so V final is 7 meters per second. Or actually, this is probably better called our maximum velocity. This elevator can get going up to 7 meters per second. So that we're asked what our time to Vmax is. How long is it going to take to start going its maximum speed? How long is it going to be accelerating for? And what is the force required to pull it up at Vmax? Because at that point we've stopped accelerating, we're going up at a constant rate. And then the last thing is how many people can we hold? What is the maximum mass of people that we can hold? How many people, how many cinder blocks can you throw in this elevator? How much mass can you add? And it still is able to operate. Okay, in order to do this, we're going to first go ahead and define a positive direction, and we will go ahead and call this our positive y direction. I like to use y for up and down. And then we're going to have some quick notes on here. They're not necessarily part of the free body diagram, but we're talking about it starting to move up. So our acceleration, when it's starting from standstill, is going to be an acceleration upwards, and eventually we're going to get a velocity that is going upwards. I would normally throw those in a different color than my forces, but I use dotted lines, so neither acceleration or velocity are force. Our only forces are these, but we have those just to keep track of what direction things are moving in. I think the last thing I want to do is I want to say that velocity at time 0 is 0 meters per second. With that, I think we're ready to start solving it. So let's talk about the piece while it is not moving. Okay, when we're not moving, we have our base equation that was added today. We have the sum of forces is going to be equal to my mass times my acceleration. Okay, I am interested in what's happening in the y, so I'm just going to go ahead and add those pieces here. So if I'm not moving, I have 0 acceleration. It's not moving. So the acceleration in the y goes to 0. This whole thing goes to 0. So my sum of forces are equal to 0. So my forces, it looks like I have a upwards force provided by the lift and a downwards force, so negative. That is mass times gravity, which is going to be equal to 0. Which means that this upwards force has got to be equal to the mass of my piece times gravity, otherwise this elevator is falling. Or if it's greater, it's going to be moving up. So in order to not move, we need to be providing enough force from this force here that we're not moving, that is equal to our weight. So we have a mass of 5,000 kilograms, and acceleration of gravity is 9.81 meters per second squared. We end up with units of kilogram meter per second squared, which is newtons. So 5,000 times 9.81 is 49,050 newtons, or 49.05 kilonewtons. So force at equilibrium is 49.05 kilonewtons. First problem solved. Okay, now we're starting to engage this piece and we are pulling it up, and this is going to be our condition while we are accelerating. So while we're accelerating, we're going to go ahead and again start with this sum of forces is going to be equal to my mass times my acceleration. My forces are the same, so I've got a positive force provided by the lift and a negative force provided by mass times gravity. Except this time, my acceleration isn't 0 because, I labeled the situation accelerating. So what is my acceleration here? So that is going to be my acceleration is going to be my force minus mass times gravity divided by mass, which is going to be the maximum force I can do. So this is as fast as I can accelerate it, is 60,000 minus mass times gravity, which is going to be, I'm going to have to do it below, 5,000 times 9.81. I'm not putting negative 9.81 in here because the negative is already taken care of by the fact that I'm pointing it down. So that is why that negative's there, and then that divided by 5,000. So I get an acceleration that comes out to be 2.19 meters per second squared. And I jumped straight to going for the acceleration because I know I'm asked for time, but what I know that I'm going to do is I'm going to pull this and I'm going to come into my kinematic equations. And in order to get time, I've got equations that look like this. I've got velocity final is equal to velocity initial plus acceleration times time. I've got x final is equal to x initial plus velocity initial times time plus 1/2 acceleration times time squared. Those are the equations that I currently have that have time in them. And what I'll note here is I've got a velocity final, I've got a velocity initial, I don't have an acceleration, I don't have a time. I don't have position, I have velocity initial, I don't have time, I don't have acceleration. So in order to get time, I need to get acceleration in order to use this. I need to get acceleration in 2 positions to do this. So it's probably easiest to look for acceleration. And with that, what do I have that could get me to acceleration? I've got my forces. I have sum of forces equals ma. So that's why we started with that. And now that we have the acceleration, our velocity final, we know, is 7 meters per second. That's right there. Our velocity initial, we know, is 0 meters per second. Our acceleration is 2.19 meters per second squared. And we want a time. I divide my 7 by 2.19, and I get the time in order to get this to the maximum height is going to be 3.196 seconds. 3.196 seconds. I've got my time. It's a little bit easier considering we only have a couple of equations here. But really what I'm looking at is I have my list of knowns. I have my list of equations, which in this case is fairly short. I know that I need time. I look at my time equations. I don't have a time equation that has all the unknowns. The closest I have is a time equation that has one other unknown, and that's the acceleration. So I start looking for an equation that has acceleration. And when you look at that, it's the one that's the topic for the day. So force is mass times acceleration will get me there. Okay. Situation 3. We have constant velocity. We're going up. We've accelerated to the point where we are going 7 meters per second, and we want to just stay at 7 meters per second. We're not slowing down. We're not going faster. Okay? That means acceleration is 0, because from that equation we just had, we've got v final is equal to v initial plus acceleration times time. If we have constant velocity, v final is equal to v initial. So we can say that that and that cancel when I subtract across. 0 is equal to acceleration times time. Well, time can pass, but acceleration's got to be equal to 0. So we're going to go ahead and pop this into my sum of forces equation again. Sum of forces equals mass times acceleration. Acceleration is 0. So I have, from my free body diagram, I get my sum of forces. I have a positive force caused by this and a negative weight. So we've got our upwards pull force, downwards gravitational force is equal to 0. That equation should look really similar to you. We get force is equal to mass times gravity, which is the 5,000 kilograms times 9.81 meters per second squared. Kilogram meter per second squared is a Newton. This is the exact same equation we had when it was staying still. So once it's moving, the force required for movement, when it's just this, there's no extra pieces going on. The force required for movement is the same force required to start it. We will do things where that's not the case anymore when we start talking about friction, but in our frictionless system, our constant velocity force and our not moving at all force are exactly the same. Okay? Last piece. How many people can we hold and still have this elevator move? Well, so we'll call this the max load situation. We have our same equation, our sum of forces equals to mass times acceleration, and we need this to move. So we need acceleration. Acceleration needs to be greater than 0. So what we're going to do is we'll go ahead and say if acceleration is greater than 0, this sum of forces divided by mass has to be greater than, which is equal to acceleration, has to be greater than 0. So our sum of forces divided by mass is to be greater than 0, or we can just multiply the mass both sides, and we can say that our sum of forces needs to be greater than 0 in order to move. Okay? Sum of forces, we have our force that we're pulling up with, and we have our gravitational force that is pulling down. Has to be greater than 0. Our force then needs to be greater than mass times gravity. I want to know what this mass is. So I'm going to go ahead and say that our maximum force divided by gravity is greater than m. Okay, my maximum force is 60,000 newtons, which I will rewrite as kilograms meters per second squared, divided by gravity, which is 9.81 meters per second squared. And did I do this in the notes? I did. That means that our mass cannot be more than 6,116.21 kilograms. Meters per second squared cancels from both of them. Which means that the mass of people in the elevator needs to be less than this minus the weight of the elevator. So we subtract 5,000 from that. That's a terrible less than. So if the amount of weight we add to the elevator is equal to or more than 1,116.21 kilograms, this elevator ain't moving. So that is our limit. Hopefully feeling fairly straightforward there. Take care.